My name is Lucas Sanchez, and this is Homework 1, Part A for Material Energy Imbalances. Homework 1, Part A starts off by asking for a phase diagram of water. So let's start off by drawing it. So on the x-axis we have temperature, and on the y-axis we have pressure. I'm going to plot a point known as the triple point to start. And the triple point of water is where it exists in all three of its phases: a solid, a gas, and a liquid. And then from the triple point extends three different equilibrium curves. And through these equilibrium curves define the different temperature and pressure conditions of each phase of water. So down here we'll have vapor or gas. You can draw it in, vapor or gas. Up here we'll have liquid. And over here we'll have solids. So each of these regions here define the different temperature and pressure conditions of each of the three different phases. It's important to note that this phase diagram here can only be applied to a pure sample of water, and a pure sample of water is one that has no impurities, so it can't contain other compounds or elements. So let's say we have a water bottle here, and in the water bottle, it's open to the atmosphere, it's an open container here. So that means air can enter into the water bottle, and we have this much liquid water. And this is air up here. So since there's air, there's oxygen and nitrogen from the atmosphere. And if we want a pure sample of water, we need to somehow remove this air and the impurities. And we can do this by boiling the water bottle. So as we boil the water bottle, apply a heat source here down here, the temperature of the liquid water molecules will increase as the bonds between them begin to break. More water vapor molecules will form. But it's especially important to note that here, at the interface between the liquid water and the water vapor molecules, we can follow this equilibrium curve, the pure component saturation vapor-liquid equilibrium curve. So this curve relates the pressure and temperature of water, and liquid water and water vapor at equilibrium. So if we increase the temperature of the liquid water, the water vapor molecule's partial vapor pressure will follow, and it'll also increase. So as we increase up the curve toward its boiling point, the water vapor molecules will eventually reach a vapor pressure of around 101,325 pascals. And this vapor pressure here of the water vapor molecules in this area is much higher than any of the vapor pressures of the water molecules up here. So naturally, the water vapor molecules will want to leave this container, going from a higher pressure to a lower pressure. So as they push out of the container here, they're exiting the container, they're pushing the air that's sitting on top of them out of the container. So we let them push the air out of the container, and then quickly we seal it off, and we give the container time to equilibrate. We have a pure sample of water. And then if we wanted to prepare a sample of water at its triple point, we would need to remove any impurities from it. So do the same process by boiling it and forcing the air out of the container. And then, once we have a pure sample of water here, we somehow need to get water in its solid phase. So we already have liquid and vapor in this pure component, or in this pure sample of water. But how can we get water into its solid phase? Obviously, we're going to do that by decreasing temperature, by putting it in something like a freezer. So we take this pure sample, this is a freezer here, and we throw it in the freezer. As we throw it in the freezer, water follows this curve here. So if we decrease its temperature, its pressure will also follow, and if we leave it in the freezer long enough, it'll eventually go down this curve here, the pure component saturation liquid vapor equilibrium curve, and it'll keep continually following this curve until it reaches a point which is around 0.01 degrees Celsius, and that's where water is at its triple point. And because we decrease its temperature so much, its pressure also drops to a low value. And as we decrease the temperature, water will begin to freeze. And we're still left with some liquid water because we'll have to remove a great deal of energy a great deal of heat from the liquid water to get it completely frozen. But we're left with liquids, solids, and a gas, all in the same container, so we have water at its triple point. And then one more application of this phase diagram here that we can apply a diagram to. Let's say we have a container that contains just water vapor. water vapor, but it has this movable piston at the top. This movable piston. So this is all just water vapor. And this water vapor is at 80 degrees Celsius. So, as we know, we're somewhere in this region here, water vapor. And since it's a water vapor, it's just a gas, so we know it follows the ideal gas law. It's a gas at low temperatures, so or not low temperatures, low pressures, so it's going to follow the ideal gas law. And then let's say we compress this boundary. And we compress it further enough where we increase its pressure, so it's somewhere along this curve here. So we increase its pressure up this enough where it lies on the equilibrium curve, the pure component saturation, liquid vapor equilibrium curve. If we compress it to that point there, we'll get a drop of water. We'll get a little amount of liquid water. And 80 degrees Celsius. It's important to note that if we want temperature to be constant here, we need to somehow cool this container, because as we compress this container here, the pressure is increasing until it gets to this point here. Once we get to this point here, pressure is no longer increasing. What's changing is, however, as volume decreases, the number of vapor molecules is also decreasing, so temperature and pressure can stay constant. Pressure and temperature can stay constant. But as we condense the water vapor molecules into liquid water molecules, they release heat, because if we want to turn a liquid water molecule into a vapor water molecule, we need to apply heat. To the reverse process, heat is released. So as the water vapor molecules condense into liquid water here, they release heat. So if we want to keep the temperature constant here, we need to keep some sort of cooling element. So we're going to say you have ice down here to keep it cool. Ice. So let's say we further condense it, and we're still keeping temperature constant, 80 degrees Celsius. We're still keeping temperature constant. We further decrease it. More and more water vapor molecules will begin to condense. So again, volume's decreasing, so is the number of vapor molecules. They're going down. But the number of water molecules is increasing. So we have a bigger amount of water here, and we still have water vapor in this area. Now, temperature and pressure remaining constant because we're keeping temperature constant, and if temperature is constant, pressure follows because they're on this pure component saturation liquid vapor equilibrium curve. If we increase, so the pressure value isn't changing as long as the temperature value isn't changing, and we're doing that, we're keeping temperature constant. So pressure's not increasing or decreasing. If we get it to any point on this curve here at 80 degrees Celsius, its corresponding pressure is its higher vapor pressure. And then let's say we compress it even further. We push it to its point where we no longer have any more water vapor molecules here. We just have water left in this container because we've compressed all the liquid water vapor molecules into water molecules. Then we can then hop off this curve and pressure will begin to increase, but not at a great rate because you can't increase the pressure of water drastically. So we pushed it past the point where there's no more water molecules in this container, or there's no more water vapor molecules in this container, it's just water. You just have water left in this container. So it's important to note that we can keep pressure in the container constant even if we decrease the volume by keeping its temperature constant. Because, like I said, if we decrease the volume here, we hold temperature constant. Instead of the temperature changing, the number of moles of the water vapor molecules will condense and it will decrease, and that will allow us to keep pressure and temperature at equilibrium as they are laid on this curve here.